Hello, my name is Amrit Saurabh Sinha and I will be presenting my master's project on secure smart contract generation. Blockchain has recently emerged as a research trend with potential application in a broad range of industries and context. Um, One particular successful blockchain technology is smart contract. So a smart contract is a program that is kept on blockchain alongside other transactions and enforces its rules without the need for third parties. Smart contracts, as far as in Ethereum, are written in a language called Solidity. So Solidity is an object-oriented high-level language for implementing, of course, smart contracts, and it is heavily influenced by C++, Python, and JavaScript, and is designed to target the Ethereum virtual machine. And as far as the usage of blockchain technology is concerned, it is being massively in R&D on areas such as voting, crowdfunding, blind auctions, and also in supply chains to track items within a supply chain with full visibility and transparency. However, despite these positive aspects of smart contracts, some problems still remain, such as the security threats involving the identification and exploitation of a vulnerability in smart contract. And also there is a legal aspect of issues as well, which is out of the scope for this project. So the problems with smart contracts. So the problems with smart contracts, well, the majority of them arise due to the most benefit factor of smart contract, which is immutability. So once deployed, the contract cannot be changed. So this means even the discovered bugs, perhaps later on after deployment, even they cannot be patched, which is quite different from the normal software engineering practices where we deploy or we present a product and we can always patch it, work it, and fix or update it depending on any further or any identified vulnerabilities or bugs that arise after production. So there is a massive need for the developers to write robust code prior to its deployment on the DLT. So smart contracts are riddled with bugs and security vulnerabilities, as a recent study of automated analysis on around 19,336 Ethereum contracts showed that 8,333 contracts suffer from at least one security issue or a vulnerability. So as you see, the issue is massive. And from here, we can see that there have been exploitations and through these bugs over already deployed smart contracts that has led to massive financial losses. So as we know that smart contracts handle financial assets of significant value, whereas as we know that in Ethereum, the current contracts of Ethereum hold around $10 billion worth of value in total. And given that how smart contracts cannot be patched once they're deployed, which means that any transaction that occurs through the smart contract on the blockchain network, it cannot be rolled back. So once a malicious transaction takes place, it is recorded and that's it. It cannot be removed. So we will see two examples. So the first one is the reentrancy attack, which was exploited in the recent DAO attack. So this exploits the functionality and the behavior of the function in the programming language of Solidity. So this is where when there's a function call, the caller has to wait for the call to finish, and this is where a malicious callee might take advantage of this behavior. So in this example, let's consider two contracts, that is contract A and contract B, where A has a wallet. I mean, A contains, let's say, 10 ethers, and it also shows that contract B, that A owes contract B 1 ether. So B can, well, it can withdraw, and let's say this is the withdraw function, where we check the balance that that so A checks that A owes B 1 ether and it is larger than 0, correct? Then it sends the ether and then it updates the balance. So let's say for this example we have an entity called Alice. So we know that contract A owes Alice 1 ether. So Alice would like to withdraw this ether. So to withdraw, the contract has a withdraw function which checks the balance that yes, it owes Alice something more than 0 ethers. So it sends the ether to Alice. Now Alice has 1 ether and the contract A had 10, now it's minus 1, it has 9 ether. Next, it updates the ether from balance 0. So that's it. Now, how can contract B exploit contract A? Now, in this case, let's consider a contract B function, a contract B with malicious functions and an entity Eve. So Eve invokes the attack function, which calls withdraw. So it checks the balance, and yes, contract A owes contract B 1 ether. It sends the ether, but there is a fallback function which takes this ether, and it also again calls the contract A. So once the contract A is called, the function withdraw is called again. Then again we check the balance and it's still 1 ether because we never had the chance to update the balance to 0 in the first attempt. Then we send the ether, then the fallback function again calls the withdraw function again. So we see that the contract B is draining the ethers in contract A by the simple fallback function, which does not let the withdraw function update the balance to 0. And similarly, the ether here is getting in contract A is getting reduced and is getting added to contract B. Now, the another example is the unpredictable state vulnerability, is where the order of the execution of function calls cannot be predicted. So no prior knowledge of a contract state during a call execution. So let's say the creator of it, let's say the seller creates an offer saying that he would give 10 tokens for 1 ether. Then the buyer accepts the offer, but then he updates his offer by saying it's that he would sell 1 token for 1 ether. So that contradicts the first call. So the buyer is pretty much getting scammed. So from all of this, we can see that smart contract security is a serious issue. As smart contracts handle financial assets of significant value, as I said earlier, up to 12 million Ethereum, which is equivalent to $10 billion. And we also know that smart contracts are widely prone to security issues, as per the automated study that I mentioned earlier, where 18.3 thousand contracts out of 19.3 thousand Ethereum contracts suffer from at least one security issue. Now, the identified causes for all of this, all of the mentioned issues, per our study and per the related studies, is due to the poor design, which has caused or has been one of the major source for security problems. Additionally, vulnerabilities also arise due to the semantic gap, and which is specific to the assumptions that developers make about executions of semantics, which is the actual semantics of writing code and solidity. So there is a formal method for software development which suffers from a gap between the rigidity of the method and the informal nature of system requirements, which developers are unaware because developing on blockchain is different from developing on generic software development projects that they have been used to. So rigorous and designer-friendly methodologies for modeling and analyzing secure software are highly desirable within the scope of blockchain technology, of course. So this project aims of providing an auto generation process by capturing and transforming business processes into smart contracts securely, and by introducing static code generation and applying various model-to-model transformations. um, uh, with a static code generation and a final security vulnerability assessment on the smart contract before its deployment. So the research problem. So the project focuses on providing an easy-to-use graphical tool for business logic modeling and applying reduction and optimization to reduce further arisal of errors that is further to use uh, that is further used to generate secure smart contract with a vulnerability assessment. So here we can see we have three components inside our SSC model where we take in the business logic, we generate a mathematical model, which in our case is a PagerNet, which which as I said earlier, we apply some optimization rules to it, which gives us an optimized PagerNet. Then this optimized PagerNet is used in our second component of smart contract generation, where we apply some static code transformation rules to generate a smart contract, which we just label it as a draft for now. And we pass this smart contract into the SC verification, which is a smart contract verification tool, which generates a SC report. So the final output, we have a smart contract with its vulnerability assessment. And this is the whole process that we have proposed. Now, the related work. As we can see, as that there has been a fair bit of work done in this field. However, we have segregated the related works into different parts as shown here as compared to our method, our SSC model, where we have the business logic modeling, mathematical transformation with some optimization, and the smart contract generation, and then the smart contract verification. So based on this study, based on these studies, we can see that there is a massive gap present uh, in the optimization of the mathematical model, which was generated through the business logic, and there's also a major gap in the final smart contract security check before deployment. Thus, this is where our study of the smart contract, the SSC model, comes in, and it fills all of these gaps as compared to the previous studies that where some do not have a graphical user interface for business logic modeling, some avoid optimizations, and some avoid security checks. Now, coming to our approach for the SSC model. As I said earlier, this is the PagerNet. So our model is divided into three components, which is the first is the PagerNet generation, the second is the smart contract generation, and the third is the smart contract verification. So the PN generation module generates a valid PagerNet. The smart contract generation uses the PagerNet and generates the respective smart contract. And finally, the smart contract verification module, it verifies the smart contract before deploying. Now, coming up to the first PagerNet generation model component, we use an AD2PN, which is the activity diagram to PagerNet model, which takes an activity diagram and converts it into a PagerNet using a set of uh, model-to-model transformation rules, which is realized via QBTO. So here we can clearly see that we have a business logic that we model in the UML designer, which is then converted, which results in a business logic in UML. And this UML model is given into our PagerNet generator, which is an existing model, which is an open source model that converts UML into PagerNets, and which generates a PagerNet draft. And we take this draft and we optimize it by performing some verification and validation checks, and then we pass the verified draft of the PagerNet into a PagerNet reduction module, which optimizes the PagerNet and generates PN reduced, which is again verified to make sure we did not introduce any logical or any more errors into the PagerNet, which ultimately gives us the PagerNet optimized. Now, for our PagerNet generation process, we have used three examples in our project of e-voting, blind auction, and rock paper scissors. So we will only be considering or going through one example, which is of e-voting, as the other follow the same pattern. So here we have the e-voting, and we model e-voting using the UML designer as I explained above, where we have the voter being registered, given voter rights, where we vet the voter per some rules such as the voter must be 18 plus, etc. Then we generate the e-ballot for the voter. Then there is vote casting. Then there is the ending of the vote. The output of our patronage generation using the transformation rules in the AD to PN model gives us the result of this patronet, which is based on the UML diagram I showed you guys earlier. And this view of the patronet is visualized by using TimeNet, and TimeNet is the tool which, since it visualizes the generated patronet, it means that it does not have any logical errors, has no deadlocks, and its syntax is valid. So the TimeNet tool acts as our verification and validation. Now, for the next step of our patron generation component was the reduction and the validation. So the validation is done through TimeNet, and we saw that earlier. But our reduction is done through these tools that we have taken from a similar study where patronet optimization takes place. So we applied these rules on our generated patronet earlier, and we reduce our patronet accordingly to generate the PN reduced. Thus, based on those rules, we identify the patronet where we can apply reduction to generate a rather reduced patronet. Thus, after reducing the patronet, we view it in the TimeNet and we check for its validation. Now, the next component of our project is the smart contract generation, as now we have an optimized patronet. So the smart contract generation contains of PN optimized, as we generated earlier, which goes through a finite state machine generator and a finite state machine PN optimize is produced, which is then used into a open source tool called fsolidm, which is a framework that allows developers to define contracts as as finite state machines with rigorous and clear semantics, which in turn generates a smart contract draft. And the parsers used in fsolidm is the one for Ethereum, which is within the scope of our study. Thus, to convert the patronet into FSM to be used in the fsolidm tool, as I said earlier, we have identified a set of transformation rules that allow us to successfully and mathematically convert the patronet into a finite state machine. Thus, after applying the rules in the previous slide, we get a finite state machine as shown here, where we have a setup node or the setup state where we can remove options for the participants, remove the participants themselves, add options and add participants. So this is after the reduction that we applied earlier. And then we have the casting, the cancellation, and then the closing of the vote. Thus, after realizing the FSM into fsolidm, we generate the smart contract. Of course, there is more required information from the developers to be provided, such as some function names, function datas, function attributes, which is rather minimal and can be used to generate smart contracts using this tool. Now, for the evaluation part. So the smart contract verification is done by a tool called Smart Bugs, which is an extensible and easy to use execution framework that simplifies execution of analysis tools on Solidity smart contracts, and it facilitates reproducibility. So Smart Bugs contains it comprises of 10 different tools such as Honey Badger, Manticore, Mithril, Osiris, Oyente, Slither. So all of these tools are included in Smart Bugs. So as a result, Smart Bugs was utilized in an empirical research to get a snapshot of the present state of the automated analysis tools for Solidity smart contracts. So we performed so smart bugs was used in an empirical study to where these 10 tools were ran through a set of database of smart contracts with vulnerabilities, and these vulnerabilities were tagged into 10 different categories. So those categories are given here, such as access control, arithmetic, denial of service, reentrancy, and etc. So, and these are the different 10 tools. So from this empirical study, we found out that vulnerabilities identified per tool were maximum by mitral, were as compared to the other tools present. Similarly, we also identified that the total vulnerabilities detected by each tool was highest, again using mitral, which was 215. Thus, so it can be concluded that the 12 vulnerabilities uh, identified by the SC verification tool was mitral, and thus we used mitral for our verification on the generated smart contract earlier. So as this was our smart contract, which was generated based on the business logic of e-voting, we will be applying or using mitral to further perform a security audit or perform a security vulnerability assessment on this smart contract. Whereas when we similarly run mitral, we get a set of exception states, errors with given severity levels as well, and function names and specific details where a bug or a vulnerability can arise or is present or can be exploited. So this would allow developers to view their weaknesses or the weak parts in their smart contract before deploying it into production. Now, the proposed smart contract model of the SSC model will be used to create safe Ethereum smart contracts in the future. However, if we are to avoid an equally high risk of security incidents, we must ensure that the smart contracts are secure by design. So, however, there are certain limitations to our project, which we will get into later on. Um, we have touched on a rather sensitive and a rather massive issue of generating secure smart contracts, which again is by design, in which we try to avoid any errors arising from the modeling stage itself. Uh, as for now, we know that blockchain-based computing systems with smart contracts are projected to have a significant or are having significant technological and economic effect. So despite increasing the popularity, smart contracts still remain a mystery to many developers, largely due to the special design and its application, which is very different from the generic software engineering practices. Thus, our method allows us to design and generate a secure smart contract that can be deployed on a supported blockchain platform, which is Ethereum, in our case, with very little or additional effort. So one of the main advantages that our method brings into the smart contract development ecosystem is introducing a formal way to visually model, simulate, and verify business logic workflow prior to the smart contract code generation. Thus, modeling the smart contracts via PagerNet helps the developers to minimize the logical errors by verifying certain PagerNet properties such as deadlocks during the modeling stage itself. Our project's working capacity is one of its constraints, as even though we use three secure smart contract modeling scenarios, real-time processes are far more complex and involve various systems and entities that require more investigation. Thus, additionally, due to the work of our SSC model, there is some amount of manual work which can take time and effort for developers to use our model, such as performing PagerNet to final state machine conversion, which is done manually through a set of rules. And this would be a huge challenge when uh, the developers would be working on larger UML model that would generate larger PagerNets, and manually applying reduction transformation rules, even though valid and mathematically proved they are correct on large PagerNets, would be taxing. Additionally, as Solidity is always changing and being versioned, The tools must be able to adapt to new versions and respond appropriately. I came across a bulk of verification tools that were not ready or flexible enough to deal with Ethereum contracts in different versions, as they were not revised or were not continuously being revised to be compatible with the newer versions of Solidity. Thus, all of these challenges further open up more areas where improvement is required and much more R&D is required to improve the secure smart contract ecosystem. Thank you.